Good morning, everyone. Today I will talk about an integration test order strategy to consider control copying. This is the outline of our talk. For interclass integration testing, a common problem is to determine the order in which classes are integrated and tested. Different test orders often lead to different test steps. A probe test order can significantly reduce the cost to construct these test steps. However, the existing measurement for stubbing cost mainly involved interclass data copying, such as the number of method invocations, but it omitted control copying, which should also be considered. In Figure 1, Class A depends on Class B, and Class B depends on Class C. The relationship between Class A and Class C can be established through Class B. Such relationship is called the transitive relationship. The object relation diagram is constructed in Figure 1b, while Figure 1c shows the object relation diagram constructed when considering interclass transitive relationships. But the solution generated by the same algorithm for two situations are totally different. Considering control copying can help to avoid error-prone and expensive test steps. Therefore, we propose ConCITO, an integration test order strategy to consider control copying. Figure 2 shows its procedure, which improves the existing methods by adding the control copying when designing a new formula for stubbing complexity. Our approach contains three steps. Firstly, transitive relationships are identified in the extended object relation diagram. Then control complexity is proposed to measure the stubbing cost of control copying for a transitive relationship, which is based on the probability of the relationship's occurrence. Finally, control complexity is combined with the existing attribute and method complexity to measure the stubbing cost. To evaluate the transitive relationships effects, we conducted experiments on 10 open source programs from SIR and answered the following 4 questions. We first determine whether transitive relationship exists in the actual programs. We count all transitive relationships containing 3 classes, such as Class A's method A1 invokes Class B's method B1, method B1 invokes Class B's method C1. Figure 3 shows the percentage of transitive relationships in all relationships. Transitive relationships exist in all programs, and in 7 of 10 programs, the percentage of transitive relationships exceeds 40%. We also set the list of transitive relationship chains as 4 and 5 respectively to study the impact of this setting on transitive relationships. Transitive relationship chains of Line 3 already identified a large part of transitive relationships, with the lowest proportion as 66% for program log4j3 and the highest proportion 100% for JBoss. To evaluate the transitive relationships effects on the generated class integration test orders, we applied our previous proposed approach to generate class integration test orders under 2 situations, that is, only considering direct relationship and considering both transitive relationship and direct relationship. The results show that changes of test orders exist in all programs, especially in program log4j3 the test probability of more than 46% of the classes differs in two test orders. Table 1 shows that the stubbing cost of test orders generated by considering a transitive relationship is lower than that generated by considering only a direct relationship for most programs. Therefore, we can conclude that control cupping could indeed affect the stubbing cost of a class integration test order. ConCITO more accurately assessed the performance of class test orders and thereby generated the class test order with lower stubbing cost. That's all. Thanks for your listening.